Hello, geeks, and welcome to Geeks for Geeks. This is Sai Prakash here, and I'm here to discuss the day 28 second problem of 30 Day Geeks for Geeks Coding Challenge. So, the problem today we are given is called as shortest range in a BST, and we are given a BST, and we have to find the shortest range x comma y, that is inclusive range. The square brackets suggest that they are inclusive range, that is x and y are also included in the range, such that at least one node from every level of binary search tree lies in the range. So, we have to return x and y such that the range x to y will be in such a way that at least one element from our level order travels, that is from level. So level is going to be this. So every time if I highlight this, so all the elements in this region are going to be my levels, right? 264 is in level. This is going to be at level 1 2 3, and it is going to be at level 4. So at least one element from that level has to be in that range, right? So if we observe here, so the answer is 6, 11, and 8 is in this range, and 10 is in the range, and 6 is in the range, and 7 is in the range, and 13 is in the range. Sorry, 11 is in the range, right? So this is what the problem statement is, and so let me say you that I couldn't solve this problem. I couldn't come up with the optimal solution on my own, and I had to take help, and I have to take the solution from the problem setter. And so the only approach that I thought is working in n square and higher. So the solution is not good to solve this problem. So I have been not able to solve this problem. So I thought, no, let's accept the defeat and let's do what's the next best thing, next best thing, right? So I feel that if you are unable to solve a problem, that's not a bad thing, right? At least I feel that. So the next best thing that we could do is like learn from the solution, read the editorial, right? So I have read the editorial, and I'm going to so I'm not going to pretend that this is my solution. So I have taken solution from the problem setter, and I'm going to discuss you and walk you through the problem setter's solution. So the solution that is satisfied that is given in the editorial, and we'll walk you through the solution, and we'll try to learn things, why they are working and how they are working, right? So this is my solution that I have taken from the solution that is given by the problem setter. So let's understand the problem statement step by step, and let's try and understand why the code is working actually, and how it is being implemented, right? So see, so there are a few things to consider here, right? So in a binary search tree, one thing to remember is everything to the left of a node is going to be less than 8, that is less than root element, and everything to its right is going to be greater, right? And in order is going to be followed in such a way that it is going to return left, node, and right. So these are some prerequisites to understand here. So the first thing that the processor has done is that he has defined a function. So this function is doing nothing but it is going to generate in order for our binary search tree to be precise. So I'm going to do the binary search tree for this, and at the same time, I'm also going to find a level at which each node is present, right? So for example, 8 is going to be at level 0, and 3 is going to be at level 1, 10 is going to be at level 1. So this function has two things to do. So one is perform the level order perform the in order traversal, and at the same time maintain another array, right? So which is going to return at what level the current node in my in order is present, right? So this is what solution is. So it is a classical in order traversal problem. So traverse left, traverse node, and traverse right. So left, node, and right. So this is a classical in order, and there's nothing new here. And at each while storing the data itself is also storing at what level it is in, right? And every time we move down the child, we are going to increase our level. So this is going to be a new level, that is the previous level plus 1. Initially we are at level 0, so root is going to be at level 0, and for every child that we are generating, he is going to be at level plus 1. Like if parent is at level n, the child is going to be at level n plus 1, right? So this is a classical recursion problem, and this is a good old in order travels, and there is nothing new here. So we have created a new two arrays called as in order and level order. So in order is going to store our in order traversal, as you can read from the comment, and even level order is going to store what is the level of ith node in our in order traversal, right? So this is going to return something like this. So if I am at node 8. So it so if in order of 8 is at index 7, like assume it is going to be at 1 2 3 4, it is going to be at fifth index, so level of 5 is going to be 0, right? So it is going to correspond, right? So at a particular index, it is going in my first in order, it is going to show me the value, and in my level array, it's going to show me its level, right? So I think it's clear till this point. And so here, so when the control reaches to this point, right? When the control reaches to 26, we have our level and in order filled, because we have called a function and it is going to fill these arrays. And I have added a print statements here, so that we can execute and and we can understand what exactly is happening there. And so this is one important thing. So we are going to maintain a new array called as a depth. So depth is nothing but it is going to keep count of what are the nodes that are present at ith level, right? So it's at zeroth level, there is only one element, so it is going to store one. And at index 1, it has two elements. It has two elements here, and it has two elements. So it's going to store what are the number of nodes at ith level. So we are going to initialize that. So we are finding the max depth. Max depth is equal to maximum of level plus 1. So if I have 3 levels, the depth is going to be 4, the maximum depth. And we have initialized 3 pointers, and the count 0 is going to be 0. So let's not look too far ahead. So let's kindly ignore this for a couple of seconds. So we'll get to that point, right? So now here, so in order to just understand, I have included this print statements, so that when I execute, you will understand, right? And the idea to solve the problem here is that since we're trying to find out x and y, we're going to take the advantage that in BST, all the elements to the left are lesser and all the elements to the right are going to be higher, right? So 8 is going to be the middle ground, and this is going to be the lowest point, right? So we're going to initialize two arrays, right? And initially two pointers, and initially a pointer I is going to be at this point, that is 2, that is first element of my in order. And pointer j is going to be at my last node of my in order. So in our case, that is going to be 14, right? So 14 left is going to be already done, so node will come after in the later case. So 14 is going to be my last node. So initially my pointer is going to be at this point, and this is going to this point. So that basically means that my range is from 2 to 14, that is minimum element and maximum element. So we are starting with this. And ideally when so this is what we're so let's keep that in mind and come to this part. So right, so this is a very critical piece of code, right? So here what we are doing is we are going to travel in our levels, and we are going to check see, as I said, at root node, that is at level so it is going to be 0, right? So if I print my depth, print my depth at this point, so it is going to be 0, because the depth for this node is going to be 0. So I'm going to do that. So I'm going to travels in my level, and I'm going to check where is my depth 0. So if I found that it is at at index k, then I know that my k is going to be the index of my root node. So we're simply trying to find the root node, and at the same time appending our depth values. And when we found the root node, we are breaking out of the loop, and I have print depth here. So this is a good time to try and submit the solution and understand it a bit better. So let me just quickly submit this solution, and I'm not going to print everything. I'm going to only print till the point that which we have discussed. So let's run this. So we have understood till this point, right? So now I'm going to print what is the depth at this point. So it is ready for evaluation. And yeah, so this is what we have printed, right? So we have printed in order. So in order is going to be my basic in order traversal. So it's going to be 2 3 4 6 2 and till 14. And this is going to be my level array. So 8 is at index, right? So index is at 0. So at index, the level is going to be 0, right? So that is what we are doing in this loop, right? So I'm going to loop in my level, and will find where is the point my level is 0. So if level is going to be 0, I know that it is my root node, and I have found my root node. So I'm going to store the index of my root node, that is k, in j pointer. So now our j pointer is pointing towards my root, and my ith pointer is pointing towards my first element of my in order, right? And if I print the depth, right, so till this point, so till the point where I found my root, so that is we have traversed all the entire left part of our array, and the depths are looking something like this. So at depth 0, that is we have one element, that is root. At depth 1, we have one element, that is 3. At depth 2, we have two elements, 2 and 6. And at depth 4, we have no elements, right? Sorry, at a depth 3, we have elements 4 and 7. At a depth 4, we have no elements, right? So because the maximum depth is going to be 4, so at maximum depth 4, we have no elements, that is 0, right? So now count of numbers where 0 node in order to j. So since we have we are going to calculate the count of depths of 0. So this is going to return me what is the count of 0. So if my count of 0 is going to be 0, that means that we have covered all the levels, right? And we have to try and change that, but that's not the case here. So once we are at this point, the count of 0, it is going to be 1, right? So if I currently picked all the levels, then I'm going to change this, right? So initially our x is going to point to this point, and my y is going to point to root, right? So now we are starting at these points, and now we'll try and move this ith pointer till it reaches root, and we're also going to move j pointer till it reaches the maximum point, right? So this is the maximum that we can do. So the j pointer, that is my second pointer, cannot move anything farther than size of in order, and my left cannot move anything greater than 8, because after once we have reached 8, so all the elements towards left are going to be less, right? So there will be no solution in that case, right? So I is only going to move till 8 in my in order. And so I'm talking in my in order, and j can move till point till the end of the in order, right? So we have this is our case. This is our exhaustion case. So we are initializing that case, and we are now trying to move these 2 pointers. So here this is where our 2-point approach comes to the picture. So we are going to try and move I and j, so that we have found best x and y till that point. So once this condition exits, we have our x and y, right? So let's try and understand it. So what's happening in this loop, right? So while j less than in order, so as I previously said, the j can reach till length of in order. So we are going to whatever we are going to do, we are going to do it in that bound itself. So in that bound, I'm trying to move the j pointer, and if at any point it is it is going out of the bound, we are breaking out of the loop, and I'm checking if I found any new level or not, right? While I am pushing my j, right? So see, j is going to move something like this, because at in order, after point 8, so in everything towards its right is going to be only pointing towards the right of this subtree, right? So everything towards left is going to be at index before node, and everything towards right is going to be greater than 8, and it is going to be towards right side, right? So I'm going to move my j pointer in this subtree, and whenever if I found a new level, that is if level of j, right? So if I found that it is going to be equal to 0, because see, we have previously seen that so level of 4 is going to be 0, but 11 is at a point of level 4, but that is given as 0 in my depth, right? So if that's the case, I'm going to decrease the count of 0 to -1. That is we have found a new level, right? So I'm going to decrease my count 0. So my count 0 is not going to be 1, because at that depth we have found a root node. We have found a node. So we are going to try and decrement that count 0, and we are going to add increase the count of depth. So depth is, as I said, depth is going to store count of my nodes at that level. So we are going to increase that to 1, because we have found a new level, right? So while this is happening, we are going to do a check, that is at any point if my count 0 is going to be 0, right? If that is the case, then we have an answer. So we have a probable answer, the answer that may be an answer, but there is not guarantee that it is answer, because our answer which we have previously might be a better answer than that. So we are going to check if y minus x is greater than my previous answer, that is previously where my nodes are pointing. If that's the case, I'm going to assign x and y to our new nodes, and we are going to break out of this loop. And this is how j pointer is going to be moved. And coming to the ith pointer, so ith pointer is, as I said, it is going initialized at initially at in order of 0th element, and it will try and move till this point, right? And we are going to check if c not count of 0 is not 0, that is it is not 1. So it is there are values which are not reached till that point, so which are out, right? So and I is in the range, so we are going to try and check for we have a very better solution or not, right? And at every time we are going to decrement our level, right? So by -1, and when we reach it to a 0, right? So we have exhausted that level, and I will know in my depth the nodes at that level are going to be 0. So I'm going to increase my count 0 to 1, and I'm going to move my ith pointer, right? So I know this is pretty hard to understand, right? So even I'm telling you, it took me like 4 hours to just to understand this solution. So I hope this made some sense. I'm not expecting every one of you to understand this problem. Is I'm telling you, this is out of my range. Actually, I have very less time today to solve. So this is what happening in the solution. So basically, if I try and sum up the solution into a couple of lines, right? So we are going to use a 2-pointer approach, and initially we are going to initialize that to now root and my initial node, and j can move, this j pointer can reach till n, and root pointer can reach till root. Sorry, the ith pointer can reach till root, and j pointer can move from anywhere from root to last node in my in-order travel cell. And at each point, I'm going to check if my answer that I have is better than the answer that I'm getting. Right? If that's the case, I am going to change these ranges, and in the end, whenever any of the case that if I is moving out of the bound, or j is moving out of the bound, so we are going to return our answer, and in the end we have a x and y. So if I submit the solution, and obviously it is going to satisfy, right? So because it is the solution given by the problem setter. So we have to remove the print statements, right? So I'm not going to even run this problem, because this is not at all my solution. But let's do it for the problem video sake. So yeah, if I submit this, then it should be a solution for this problem. But trust me, this solution was way out of my head, and so yeah, to be honest, it is it could be probably the best problem till now. So yeah, it is the hardest problem, but as they say, the hardest thing is the best thing, right? So problems like this teach us more than problems which are easy to solve, right? So, and if you observe that from the past 3 days, we will be given trees on our binary trees, and the level of complexity has been increasing till day 20, right? So we had a problem called as corona vaccine yesterday, which is a good hard problem, and previously we had Valentine sum, which is also a hard problem, but it was easy to solve since we know how the drivers are working, and this is how you can try and solve this problem. And I'm sure some of you have not solved this problem on that day, and I ask you one thing, don't feel sad or anything, because see, the problems like this test us more than problems which we solve, right? So yeah, that's it for this video. I have nothing more to explain here. So I hope this video was kind of helpful, and if that's the case, give a like, and Subscribe to Geeks for and keep watching and keep solving this problem.